All right, we have the second semester of Fundamentals of Electronics, Basic Electronic Circuits, EE213. Same text, and this is the first of 3 videos on Chapter 11. And that chapter is going to be about power analysis AC. This and Chapter 12 are both on AC power, discussing power, how it's delivered, how the energy in it is calculated, all that and so forth. But it's the beginning of frequency analysis, which we'll take up, in Chapter 13 and really the rest of the book. Once you have the sinusoid involved, there's just a lot of interesting things that happen. But the most important sinusoids in our daily life are the deliverance of power, and that's a single frequency, whatever that frequency is. 60 hertz here in the United States, 50 in Europe, and maybe different elsewhere. That power analysis is very important. So we're going to devote 2 chapters, 11 and 12, to that. And this is sections 1 and 2 in Chapter 11. Okay, so if I can get things to operate correctly. The first section is on instantaneous and average power. So this is just introducing power, okay? Introducing power to us. So here's that fundamental equation. Fundamental, I say, it's really the obvious one. Voltage times current is power. Here's the voltage that we're going to use, right, in our analysis. Whoops, right there. It's got a magnitude, a frequency, and by the way, the frequency, this is not 50 hertz. This is omega, right? And just as a reminder, omega is 2 pi times the frequency. So this is your 60 hertz, and 2 pi is about, 6 plus times that. So it's going to be, some number more like 370 or 380 when you actually get down to doing numbers. Okay, and then there's an important offset here, theta, right? So if I'm thinking of how this cosine is, right? Remember, the cosine starts at 0 degrees, it starts high, and then it goes right like this. But this would be theta equals 0 degrees. There's no offset. If I have some offset, what happens? The theta is going to move this either back here or over here, depending upon the sign, plus or minus, right? So you might think about, what does a plus sign do if I have, say, 20 degrees and it's plus? All right, then when time is 0, this is actually going to behave like it's already down here. So this is the plus side, and that's the minus. All right? Think about that. If time is 0, in other words, I'm on this axis. If time is 0, then it doesn't matter what the frequency is. If time is 0, I have the cosine of theta. And the cosine is going to fall in the first 90 degrees. So in other words, I have to be right here. So it's a little confusing looking, all right? But just keep that in mind. So you'll see these things come up now and then. Current is the same way. You end up with a magnitude here. You're going to have the same frequency, right? Got to be the same. The current voltage have to be the same in AC analysis. You now have a different phase angle, right? Voltage phase angle, current phase angle. Theta sub V does not have to be theta sub I. It might be, maybe, in a, what, where will these two be the same? In a resistive load. The thetas are equal. Okay? The resistive load, they're going to be equal. Okay, so now if we put this together, our simple formula, now all I've done, or all the book has done, is just take these two values on this side and put them together in the obvious way. And you say, oh, well, that's wonderful, but this already looks bad to me. I've got now the product of cosines. So right away, we know we're in trouble unless we remember a lot of trig, or we keep a book handy at our elbow with trig formulas. You're not going to need a ton of them, but the ones you do use, you're going to use over and over again. And just as a heads up, you know when you have phase angles involved, it's sort of a lead in to the word phasors, and we're going to have phasor notation, right? So things like this can be called cosine angle theta v, where this is understood, omega t is understood, phasor notation. The dealing with phasors, which is, you know, the fancy word or another word for vectors, and vector addition, that kind of thing, vector multiplication. We're going to have a lot of that throughout AC power analysis because we've got a single frequency, right? So that's pretty nice. All right, here's the trig function that's going to help us out here. The simple one is, and these you can all look up online, or what have I got here? I think I lost my pen. You can look these up online or get a simple trig reference book. But here's our A, right? Our A is this, is A, and this guy likewise is B. Okay, so now when I put the product together, oh look, the nice thing is I'm just adding and subtracting A and B. So how will that be? If I subtract the two, I'm going to get omega t minus omega t. It's going to go away. So that'll be phase voltage minus phase current. Right? We'll end up with this little term. This is going to be phase voltage minus phase current. And this, A plus B, will be, oh, now we get a double frequency. Somehow the frequency is going to double, and we'll end up with phase of voltage plus phase of current. Okay? So you can see this term, that net phase angle is going to be smaller. In this term, the net phase angle is going to grow. So if you picture here, you got two vectors, they're going to come closer together, right? Where this is minus the other phase. These two, they're going to get wider. Plus. Whoops. Okay? So that's just an idea. And also the frequency went up here just a whole bunch. So, well, I've written over, but here I just copied from the text. You can see all that that fanciness. Now let's look. You know I'm a big picture guy, and if it's critical to relate the math that you write and see to the picture that it creates, or vice versa. So you use the pictures as analysis tools. I'll take this picture out of the text. It's a really good one because look what it shows us. It shows us the obvious things here. Here's going to be a frequency component, right? And this is going to be the amplitude right there. And then it's going to show us, so that's the frequency component. What you don't see from this, well, you kind of do. There's the period is now doubled, right? But that's inconsequential because we don't know what omega is in the first place. If we put this on the same graphs with voltage and current, we'd see this is twice the frequency. The important thing is there is a there's a magnitude, and now there's an offset. Only look at this. The offset isn't just the magnitude. The offset is the magnitude times cosine of something. So what is this? This is almost like a DC term. It's an offset. Look what happened. The zero line, which we're used to seeing on sine waves being down here, the zero line has been jacked up by this much. So what's happened in power? I take voltage and current of an AC signal, and the instantaneous power has now been lifted up, so that a lot of the power signal is all positive, right? So I don't have it. This is a little bit of negative power here. Most of it is all positive, right? So that's energy being delivered. That's what's going on there. That is energy being delivered. Okay, so let's move on then to. I'm going to keep that waveform, that illustration, because it is a nice one, and we're going to talk about now. Average power. You see the raw power, there it is right there. And we'll be analyzing how far does that center line move up and down as we go. And we're going to want to play with that by the end of the chapter. So here is averaging anything. Here's that average power. Two terms. What is it we have to deal with here? We got to deal with my pen that doesn't want to be a pen anymore. Wants to revert to a cursor. So this is not the complete power. All I did was take the instantaneous power equation and say, if I want the average power, I have to calculate the average. I have to calculate the area under one period. So I got to go through all of this from here to here, right? I got to calculate, I got to get all this area in here, right? All that area I got to get, I got to subtract that little bit, and then I got to divide it by t, the average. So here's that first term. And remember, all of this is a constant value. All right. And then so that's a constant times dt. So that's going to be, in the end, that's going to be a constant. I mean, you can already see where this guy is going to go. So this whole thing is going to be 1 over t, times what? A constant k t, the integral of dt is t, evaluated from 0 to t. So this is going to end up t over t, this is going to equal 1, yeah? Or k, right, I should say. It's going to equal k. We'll anticipate that. That's a good thing. Here's the other term, the one that has a little more time value to it. Here's this same constant thing going on. Maybe I can do this way. Ooh, look at that. The same constant thing going on, only now we have a cosine, we have a time varying term that has to be integrated. Okay? And we can do that easily enough. So here is that term. This is the first term, right? I did that for you. I called all of this stuff here K. All of this I called K. And then it's times 1 over 2. So I've already done all that integration for you there. You can see that. The second term now looks like all of this, right? And if we follow this through, we're going to get, oh, we just get the constant portion. Okay, we only get the constant portion. Where's pen here? Come on, help me out. There we go. Okay, that's all that's left. Why? Because the average value of a sine or cosine is 0, right? The average of a cosine equals 0, right? Because this piece now, this whole piece that we're averaging is not this, we're actually doing this. We're actually integrating this signal, right? This is the offset. This is the offset. And this is the sine wave. Well, the average of a sine wave here is 0. All right. So this whole second term is as nasty looking as it is. We don't even need to think about it. You can go look up the value of that in a table and you're going to get 0. Here's what we're left with, the offset value. Right? So all of this, you can imagine everything under this dotted line is the real power. That's the average power in this circuit. Okay? All right. So now we've got instantaneous and average. Let's see. I want to talk about. So I want to before I leave this formula. This is now our average power, right? I want to remind you there's other ways to show this, and here's our vector phasor equivalent of this, right? The 1/2 VMIM, and then you only indicate the phasor angle. Now what's nice here, of course, is the frequency is gone. It was gone in the first place, but just because it's gone doesn't mean you can't indicate it as a phasor. And if we go back and think about when we talked about complex numbers and complex representations, this whole item can be reduced or expressed. It's not really a reduction. What have we got? We've got 1/2 V times I, what is this thing? Conjugate, right? So that's going to be kind of like the inverse. Let me indicate here. Let me show you. I'll expand that out. If I were to take this term and write it as a complex number, which it's a representation of a complex number. Remember, this is some magnitude, 1/2 VMIM, times at a phase angle of V minus I. Okay, but I can represent that. So let me do this, just so we know this is real, and this is imaginary. And let's say here's this representation, right? So the length here is 1/2 V max I max. Those are the maximum values. This angle in here is theta V minus theta I. Okay? So what does this mean? If I do the projections down here and over to the imaginary axis, I can write this as an imaginary or a complex number. And that's all that's happened here. Here's the real part. They both have the same magnitude. Here's the real part. And here's the imaginary part. Right? And really, the sine and cosine then represent the fractions of of the magnitude vector, the fractions that are real and the fractions that are imaginary. These kind of pictures you're going to want to get a hold of, because they're going to either facilitate or haunt you throughout this whole business with AC voltage and understanding power and so forth. Because you can see the more I change this angle, the more I could rotate this way, I'm going to have a smaller and smaller real component. The more I rotate it toward the real axis, the more real energy I have. And the bigger term I have there. Okay, so I just want to take that extension and keep on that. All right, now we've got instantaneous and average power. Now we want to know, if I have average power, how do I get the most of it into my load? The most. I want to maximize it. And our old friend Thevenin is back. You might remember Thevenin and Thevenin equivalent circuits. Okay, we could have, you know, just let me draw a simple one here. We've got a battery, right? And this is the load R. And these are the terminals. If that's the Thevenin equivalent, right? And I say, well, how much power will get out here? How can I deliver the most? I'm doing this strictly in terms of DC now, right? If I want to get the most energy out here, how do I do that? And you might have to go back and refresh on Thevenin equivalence, but it happens when you put a load that's equal to, this is the load, and this is the source. When our load equals our source, I get the most energy out. And you can play with that, right? This is a simple, if this is voltage, the voltage on the load is going to be RL over RL plus RS times the voltage of the source. And you say, well, why don't I just keep jacking up RL? But RL is also in the denominator. And I'm not going to review that power transfer, but when the load matches the source, you're going to get the most transfer out. All right, so now all that happens now is we're going to take this, and instead of just saying, you know, our Thevenin, not just resistive loads, now we're going to add reactive loads. A Thevenin reactive load, and if it's inductive, it'll be plus JL. If it's capacitive, it'll be minus JL, right? So this side is for the inductor. Okay? Whereas this is the generalization. But all we're doing is taking this picture up here and saying, okay, this is now Z, and this is now Z. Some complex load, okay? That's what's happening. And the current is just V Thevenin, same formula I just did, right? If I took my little formula over here that I wrote, right, we could find the current is equal to the voltage, right? The voltage divided by the total resistance source. And my source is the Thevenin here, so, but it's the same thing going on, except now we've generalized it in terms of complex numbers. So if we plug all this stuff in and get, you know, really grand about it, we can continue to collect things together. We got the Thevenin equivalent, resistance, the real part, and the Thevenin equivalent reactive part. Okay? So the next obvious step, or maybe it's not so obvious, but is you want to take the real parts and the imaginary parts together, right, and get things grouped the way they would be. So you'll have R Thevenin plus R of the load, which turns out I'm calling it inductive right now. And most loads, by the way, I'll point out in later sections, plus J times X of the Thevenin plus X of, of the load, right? So that would be, the current is this. Now, if I want to talk about the power of this, right, now that I've got it all grouped, if I want to talk about the power here, what do I want to do? I've got my basic, here it is, right, 1/2 I squared RL, but this capital I, right, is the vector I, okay? It's the magnitude of I. So it's this I here, right, which is a full magnitude. These are actually vector quantities in disguise, right? They could be written as phasors. There is an angle associated with all of this. So here it is with all the pieces put together. If I square this, 1/2 RL over 2. So here's that, right? That's this piece and that piece. Now I got the nasty I squared. So the V Thevenin squared, here's that. Let's examine the pieces, right? That's right from here. Now I have this whole bottom squared, and somehow you're telling me that reduces to just the square of each part? Let's try it. We know it's going to be this squared. So let me do it this way. A plus JB, right? That quantity squared, right? So what's this? This is A squared plus, what is it? 2 A squared plus 2JAB. Okay, I gotta fix something here. As soon as I wrote it, I realized this isn't what we're saying. This isn't right. All right. When you have this, this, if we look back, this, if you have complex numbers, this actually becomes current times current conjugate. That's my bad. I should not have just taken it as a straight square. So that means if this is A plus JB, and I want to square it, or I want to take the conjugate, then it's times A minus JB. And so what is that? That's A squared plus JAB minus JAB minus J squared B squared, right? So this cancels that. J squared is minus 1, so this all becomes A squared plus B squared, and that's how we came to this. This is B squared, this is A squared. Okay? So it helps me to work through some of these little things rather than just take them at face value, because then you get familiar with what's happening in detail. Okay, so here's our equation now. I just copied it from the previous page, right? And we're going to break this up into two parts. What's our goal? Our goal now is maximum transfer. Remember the goal? Maximum transfer. Average power. So here we've got average power in terms of our maximum, right? So Thevenin made it maximum. This was Thevenin, and to maximize we did Thevenin, and now to get our average, transfer of the average, right? We have our, this gave us that, this gave us our average. Now, how do we maximize it? We have the right circuit. How do we maximize it? We set partials equal to 0 and solve. Okay. We have two problems. We got to solve for a real part of the load and a reactive part of the load. Okay? So let me do those in two parts. The real part comes, we take the the reactive part, we take the partial with respect to the reactive part of the load. So here is that, right? Nothing here, nothing here. This you'll have to look up, right? I'm not gonna dig out all of the math here, but this is just a lookup. What's the differential of this with respect to XL? You're only dealing with the one variable. So the partial with respect to XL is this. The partial with respect to RL is that. Ooh, a lot longer. A little more of a hassle there. Okay? So, to maximize, we set each one equal to 0. Right? So the partial with XL with respect to 0 and the partial with RL, we set them equal to 0. Okay? Now, when we do that, what is it that we're actually going to end up seeing? Okay, so you can see right away here, almost by inspection, if I set this equal to 0, it's only the top. Here's the only term that can make any difference. You're really setting this term equal to 0. So that partial becomes 0 when x Thevenin is equal to minus x of the load, or vice versa. You can attach a load that's equal to a negative x Thevenin. So you can see, by the way, what's going to happen there. This is going to want to cancel the reactive part of the source so that you get all real power. Right now on the other side, the whole thing goes on a lot deeper, right? All of this, we know now what's going on here. So all we're concerned about is getting this upper piece, equal to 0. All right, it's the only way this can be made 0 because the Thevenin source is a real source. Okay, so what happens here? X Thevenin is equal to minus XL. So this term goes to 0. So now I've got R Thevenin plus RL squared minus 2RL times R Thevenin plus RL. Okay, so let's just try it. For kicks, we've got R Thevenin plus squared, I'm just squaring this first term, plus 2RL R Thevenin plus RL squared minus 2RL R Thevenin minus 2 RL squared. Okay, so that's equal to 0. So what have we got? We got 2RL R Thevenin minus 2R. Those cancel. I got plus RL squared minus 2RL squared. So that will take out one of those. So this gives me R Thevenin squared is equal to RL squared. And we get that for maximum power transfer, we'd have to say, what? Thevenin is equal to RL, which is sort of like what we knew intuitively just from the basic Thevenin equations. If it was only real load. So maximum average power happens when we're able to basically get rid of the reactive part and end up with a strictly real part in the Thevenin sense, just like DC. Okay? So we can think of this as just the load and the Thevenin equivalent. They're not really equivalent here, but so this is somewhat of a suspect equal sign that's thrown in there in the text. If the load is the conjugate of the Thevenin or vice versa, that's what we want. Okay. All right. I think I'm going to quit at this point. And quit at this point. And I will say that what we have here in the bottom, what we're saying is that the maximum average power transfer occurs when the load is the conjugate, the complex conjugate of the Thevenin source. Okay, and when that happens, the maximum power that's delivered, the maximum average power, is the Thevenin voltage, the magnitude of the Thevenin voltage squared, divided by 8 times the Thevenin resistance. And you can crank out all the math for that if you really want to, but it's similar to what we've done before in the past. Okay? So this is what I'm going to say about sections 2 and 3. Go on from there. There's some problems to work, and we'll continue then with sections 4 and 5 in the next video. Thanks.